Okay, welcome everybody. This is going to be a quick tutorial on magnetic fields. So one of the things I want you to keep in mind is please bring with you your prior learning. We have completed our gravitational fields, so you should be very comfortable with identifying and calculating using this formula. And please make sure you can also draw the field lines for gravitational fields. So remember, your source is anything that has mass. The larger the mass, the larger the field. It also, again, all of those field lines will always go towards. That's a super important key summary. You've also spent a fair amount of time looking at this magical formula of being able to calculate electric fields. Now, again, with electric field lines, those are a little bit trickier. So please make sure you know a few key concepts. Number one, you will always have field lines traveling from positive to negative. Always. And you can always tell what charge your source is by using a test body. So if I have an unknown source, not sure what it is, but I will be given field lines. So maybe my field lines look like this. I know the basic law of attraction that if I have two like charges, so maybe it's two negative and two positive charges, these two will repel and they'll push away. If I have an opposite, a positive and a negative, these two will attract. And that's all you need to know when you try and figure this out. So if I, again, am not sure, I have these field lines given to me, put a test body anywhere near it, and look what happens. I'm getting a repulsion on this one. So I know this has to be a positive charge. If, again, I'm given another unknown, but all of a sudden I see these field lines going towards, similar like this. Again, I'm not sure what it is. If I put a positive test body here, I now have an attraction. I have this one, so I know that this is a negative source. So it's going to be really important, especially this concept of which way those field lines will connect, and it's always positive to negative. So as we magnetic fields, what you need to understand is essentially what makes a magnet a magnet. And I have a few videos that are listed on the video of the week, so please make sure you go and watch those. But essentially, if I were to take a look inside any magnetic material, so specifically something like iron, most of you know iron is magnetic. If I were to look at its molecular structure, there are certain things inside of all materials, specifically if you are on your periodic table and you are those transition metals. So again, everything on the left side, we are metals, but not all metals are magnetic. There are a few that kind of sit right up here at the top. Iron is one of those. And essentially, if you were to take a look at how its electrons fit and where they can basically spin, they have a very unique way of lining everything up. And I'm going to show you what I mean in the next slide. But you've already experienced this. Because if you ever take two magnets and you align them in a certain way, they seem to attract and pull together. Okay, and that's because you have two opposite poles. Again, similar learning we've done is think of your electric and negative charges. Think of this as a positive and negative. So think of your north as your positive electric field or source, and your south pole as your negative. Easy way to remember this is think of S and subtraction, okay? And again, there's always a pattern. So if I were to flip these magnets around and now have north facing north, I know they're going to repel. So very similar things where like charges or like poles will repel, and then opposite poles or opposite electric charges will attract. Okay, so that's an important summary going forward. Actually, take a look inside these magnetic materials. This is actually what you see. So imagine if I had iron and I could actually take a look at its electrons, the way that they sit. And again, reminder where this is on your periodic table. They sit sort of right here, and they have a unique electron structure. So inside, there's something called their domains, and they all line up, and they all basically point in the same direction. Now, one of the things I want you to be careful when you look at this picture, I have arrows going south to north. That just means they're aligning. We're going to learn there's a very important way of looking at magnetic fields, and they always create closed loops, but it's always north to south. So this is just showing that they all align in a certain direction. Now, if you want to, there's a great video, and it's called How Do Magnets Work? And I suggest you basically watch that. Here's the basic summary you need to know. So with a magnetic field, and we have one of these definitions and sort of a summary for every single field, okay, I need to, again, have a magnetic source. So again, that goes down to an atomic structure, okay? Or I can create a magnetic field, and we'll see that later with using a bit of electricity. Again, they are always going to work from north to south. So if I were always going to draw a magnetic field, okay, I would draw my field lines, number one, in a closed loop. I wouldn't just draw an arrow. I'm going to draw a closed loop, and you're noticing I'm drawing it north to south. This is an absolute vital summary, okay? It's always north to south. Easy way to remember this is the N comes first in the alphabet, and it's always N to S, okay? So that's an easy way to remember this. So the reason it's important is I can now do a lot of applications for this. So if you were to take a look at a bar magnet, or what we call a permanent magnet, that's what these are, and I'm going to show you a few videos with these in them. I can actually show you those field lines by putting a test body in them. Now, we've been using test bodies before. Now, a test body here needs to be something that can be affected by a magnet. So I'm using a compass, okay? And so most of you know that a compass needle will deflect in a magnetic field. And you'll actually notice that the way that these magnetic needles are forming is they are forming a closed loop. Now, this, again, is a super important concept, because what we're going to learn in a little bit is I can actually take something and I can cut this field in half. And if I can cut or work perpendicular to this field, so at 90 degrees, I can do a lot of really cool things. And that's essentially how your generators work. So we're going to take a look at that a little bit later. So please make sure you know how to draw a field line. And again, I have a few videos embedded that I'm going to show you. So always north to south. And one of the applications of this is we have a magnetic field around us. So this is basically your Earth. And we have, again, a molten iron core in the middle of our Earth that basically spins. And by spinning a sort of a magnetic material, you'll actually create this magnetic field. Now, it's interesting, and I want you to kind of take a look at this. If I were to retrace these drawings, I have it going from the bottom of the Earth to the top. That's the way that these field lines are moving. So that's interesting that it's going from the bottom to the top. So it's going this direction, okay? So what I want you to do is think about this when we get to this concept of how this magnetic field works. I always know that magnetic field lines always flow from north to south. So one of the questions I'd ask you is, this is the bottom, this is the south pole. Why is this where it's beginning? So that's an interesting question that we're going to try and answer. So to help you sort of understand this, I have embedded a few videos. So let's see if they will actually work for you. Okay, so here's a permanent magnet. You're going to see that there's a north and a south pole. And if I were to superimpose and just lay over top a bunch of iron filings, we know that iron filings are magnetic, you're going to start to see those field lines starting to show up. And you sort of see this sort of ripple effect. So right here, you're going to start to see the iron filings start to align, and eventually it's going to form a closed loop. And again, it's always going to go from north to south. Okay, so for this video, you're going to see that I have two north poles. So consider this sort of two positive electric poles facing each other, and see if you can predict what would happen if I, again, were superimposing my iron filings. You're going to see, again, that this magnetic field, they're going to repel, because north and north will push away. So you're going to start to see this void starting to exist where the two meet. But again, you're going to see on this side that the north always wants to go to the south, and again, the north always wants to go to the south, which is kind of a neat phenomenon. Okay, and here's the last combination. So again, I have a north facing the south. If I again superimpose, this is one that's probably the most spectacular to see. You can again see you have those closed loops forming, and again, you're getting north to south, north to south. But what's even kind of more of an interesting phenomenon, if I sort of screen out, this north will also eventually create to this south as well. This pole will create a closed loop if these magnets were strong enough. And here, so as we move forward, see if you can actually apply what we've just learned. So if you need to pause this video, and then I'll show you how to draw in your field lines. So again, how you draw in your field lines, always find your north. Start with your north and make a closed loop and have your arrowheads, your vector lines facing the south. And again, I need to have two. So I need to make sure I draw in two field lines. So that one's pretty easy. Then when you have combinations, again, start with one combination. So we just saw this in that video. So again, north to south, and again, north to south. But then I also have one here, north to south, north to south. Okay, so again, the stronger the magnets, the stronger that magnetic field. No different here. I could draw again those field lines working both ways. These two are going to repel each other, all right? So I would actually see this, and this is that repulsion here, and that is that repulsion here. So I actually can draw in 4 field lines for this one, which is kind of an interesting concept, and this would be my last one, okay? So again, this repulsion here is going to create that void, and no different here. So if you just wanted to draw in the basic ones, again, I'm going to have north to south on each of these individual ones. But then this field line on the right-hand side, we'll also want to make a closed loop here. And I would see this and this to this one. Okay, so field lines can be quite dynamic. Again, what we're going to see is if I were to cut this field line in half, so again, this is a pull, there's an attraction. If I were to cut this, I can actually use sort of where this push and this pull is created, I can now use. So one of the things that's really important about this concept is that I can actually also create an electric field by running a current through a coil of wire. So if I have electricity, running through, say, this particular wire here, okay, and if I were to wrap it in a coil, okay, so I have running electricity, what I'll actually make is a magnetic field. And that magnetic field will, again, run around or run through. So this is called an electromagnet, and it's a super important concept. So essentially, if I wanted to lift a very, very heavy car, I can actually create a magnet here by basically running electricity through it. Okay, and that way I can now lift something as large as a bus or a truck because I can actually make this magnet stronger or weaker. And here's how I can do it. Number one, the coil of wires. I can have just a few, or I can have many wrapped in a tight coil. This is going to be a stronger magnet. The actual current flowing through there, the higher the current, okay, so if I keep increasing my current, or I keep increasing the number of electrons running through, again, the higher the current, the stronger the magnet. And I can also reverse this magnet. This is super useful. So remember, in permanent magnets, we know it always goes from north to south, north to south. But what's the amazing thing is if I can actually switch this, that if I switch the electricity moving the opposite direction, I can now make this the north and this the south. And why is this important? Basically, the concept of motors and this ability for something to spin is entirely based on this concept where I can take an electromagnet and I can flip its polarity, or I can flip its north to south, and you essentially constantly make a push concept, and that's essentially how your motors work. Okay, so one of the things that you need to appreciate is that you're sitting essentially within a massive magnetic field, and this is the Earth magnetic field. So again, how this is created is inside the core of our Earth, we have a moving magnetic material. So you have an iron core that essentially cycles, and when you have a moving magnetic material, you're going to create these field lines. So one of the things, again, I want you to sort of really notice is that they come out of the bottom. So we would know this as geographic south, and then at the top would be geographic north. So we've always seen this on maps, but this is magnetic fields. So there's a problem here if I were to label my globe as such, because I have field lines moving from the bottom here to the top. And one of the fundamental things we know about field lines is they always create closed loops from north to south. So see if you can solve this bit of a problem before we move to the next slide. So hopefully you've figured this out in that you have two different concepts. You have geographic north, but then you also have magnetic north. And so we have two different north poles. So if I was going to go back into my early childhood and into where I have learned my social studies, I know that the North Pole is at the top and I know that the South Pole is at the bottom. But this is geographic north, okay? And that's just an arbitrary sort of distinction that was given. But if I were to look at the deeper scientific understanding, I know that my magnetic pole, the one at the bottom, is my north magnetic pole because these field lines create from the bottom up. And the reason I know this is we actually see actual evidence in our sea floors. So one of the things that we have seen, and this is sort of through our mid-Atlantic drift. So essentially, if you were to take a look at North America, here on the left, right? So here's North America, and then you have Europe on this side. In the middle is the Atlantic Ocean, and you actually have two seafloors, and they're spreading this way. Okay, one is spreading towards Europe, and the other is spreading towards us. And this is one of the largest mountain chains in the world. But one of the interesting things is if you were to take a look and take samples of essentially the alignments that are in the floor, you actually see that these poles are flipping. So I can actually take a sample of the sea floor, and I can actually test its domain. So it's how those magnetic lines are basically aligned. And we actually see this pattern, we see it flip. So currently, our magnetic north is on the bottom, okay? And our magnetic south is at the top. And this actually makes sense, because if I were to hold a compass, right? So here's my compass needle. It always points to the north if I look about my compass. But in order for that to do it, its thing that it's attracted to must be the south. So that's how I know that this is my south magnetic pole, because my magnets are always attracted. So remember, it has to be the opposite, which means that my north pole is got to be on the bottom. And again, this is my magnetic north, because north and north would repel. And that would make sense that these are pushing away. So that's kind of a neat thing that you can actually apply. So the reason why this is a very, very important thing, and again, there's another great movie on Video of the Week that I want you to watch, is essentially because we are very next to a very active sun, there are charged particles that basically the sun will throw at us, and we have basically a deflecting field. So this magnetic field will actually deflect these very intense charged particles, and we need that. Now the problem is there's a little bit of a chink in our armor because we sit on a ball, we sit on a sphere, and because these closed field lines, they have to kind of enter and exit, there are a bit of a gap here on the poles. Now here in Canada, if you kind of look where we are, so if I did an amazing drawing of North America, in Canada, we are basically exposed to this. So this is kind of where this gap is. So because of this gap, you get amazing things like northern lights. That's why we can see them a little bit better, because these are basically these charged particles skipping in on these gaps, which is pretty amazing. And in the 1980s, there was an amazing electric storm. Your sun was very, very active in the 80s, and it was a massive blowout. So consider sort of the energy and the particles coming at us were absolutely massive. And it actually blew out our entire banking industry for a week, because all of the satellites that were there were basically interrupted. And so Canada was in the black for a while in the 1980s. So that's one of the things that NASA and NOAA, which is an organization that basically looks at the solar energy and the solar discharges. And we're going to learn more about this in our next section when we learn about unit or outcome 3. We're going to appreciate the energy that the sun throws at us. And thanks to our atmosphere and our magnetic field, we have a defense mechanism, but we're going to take a look at this. So again, this is a great video. Please watch it. It is going to be in the video of the week and in your notes. And there's also, it's basically from NASA, and it shows you how the Earth's magnetic field will basically help us protect us. We have a cool phenomenon. So the last thing I want to show you is if you take a look at this power of magnets. So your entire world is bound in electricity. So if you were to take a look at this connection, we know that electricity is essentially electrons that are flowing through a wire. Now, you have to consider where these electrons come from. So an electron is a charge, right? And we know that, but there needs to be a source. So we know if we take a look at magnets, right, we know that where they kind of get their unique magnetic ability is if I were to draw their electron, it's kind of how these guys spin. So these two concepts are very, very, very much connected. So this was Michael Faraday, and we call this electromagnetic induction. So what it does is it takes this idea of a field line. So if, again, I were to take a look at a magnet, okay, I know that a magnet always flows from north to south, right? And I create these closed loops. Now, the amazing thing is if I were to take a wire, so if I were to kind of create this, okay, so imagine a magnet in there, but I were to create a wire that can cut, again, 90 degrees to these field lines, what I basically do is, again, that spinning sort of field that was created by these electrons in my magnetic material, I can actually release these into basically an electric wire. And that's exactly what happens. So I'm going to show you actually how this works in real time. This is a video I did that basically shows you electromagnetic induction. Okay, so in this video, I'm going to show you essentially electromagnetic induction, where electricity and magnetic fields can actually now produce running electricity. So you have three items here. You're going to see a solenoid, or basically it's a very large coil of wire, and I've attempted to give you where the positive and negative end will basically run. This device in the middle here is a galvanometer. It basically allows me to see current running through it. So if this needle flicks, I have running electricity running through there, and then I have a permanent magnet which has a north and a south. So one of the things that Michael Faraday figured out is that if you take a magnet, there are magnetic lines, and I know that those magnetic lines go from north to south, and they form a closed loop. Now, what this arrow is on the solenoid is essentially, because this is a coil of wire, this magnetic field can be cut, and then I can actually release that field, that force that's produced, and I can now create electricity. So if you watch, if I go through the middle of the solenoid, I am now producing running electricity. And one of the things I want you to note is I have the south end going in through the positive terminal. So if I'm going in like this, you'll see how the current goes in the opposite direction. And then if I pull out, it goes to the left. So if I push to the, if I go into the left, it moves to the right. And if I pull out to the right, the needle moves to the left. And they work in opposites. But essentially, this is what a generator is. If I can somehow move a very large magnet through a coil of wire, or move the coil of wire around a magnet, I can basically capture that push and pull that's in those fields, and I can now create electricity. So this is essentially how you are charging your cell phones. This is how you are basically running your everyday life, and this is electromagnetic induction.